In this week's video, we're going to check out MPLS, Multi-Protocol Label Switching. Hey, this is Kevin Wallace and welcome back to the channel. And if you enjoy this video, please do me a huge favor and click like and also subscribe so you don't miss any of our weekly content. Now, what specifically are we going to be covering in this video? Well, we're going to begin by taking a look at the MPLS 32-bit header. It's called a shim header because it injects itself in between layers 2 and 3. Sometimes we call it a layer 2.5 header, and we'll see what's in those 32 bits. We'll also talk about various MPLS terms, such as an ELSR, an Edge Label Switch Router, an LSR, a Label Switch Router, and my personal favorite, penultimate hot popping. But most of this video is going to be focused on configuring MPLS. We're going to have a customer going across what we're pretending is a service provider's network, and we're going to see how the MPLS cloud makes forwarding decisions using labels and also can assign route distinguishers to traffic so that we can keep one customer's traffic separate from another customer's traffic. And after watching the video, if you want to try this on your own, maybe while watching the video again, we've included a link in the description that's going to allow you to download a zip file which contains the topology that we're using today, as well as a .yaml file which you can import into your copy of CML, Cisco Modeling Labs. Or you can go out to Cisco's DevNet Sandbox and you can reserve as much as 4 hours at the time of this recording on their sandbox running CML, so you could actually use CML for free. And if you want more information on that, there's a link in the description to another video I've got that explains how you can use Cisco Modeling Labs for free out at the Cisco DevNet Sandbox. Now, before we get into today's content, I want to let you know about a free PDF ebook that you can download. It's called 4 Ways to Get Hands-on Practice for Your Cisco Exam, where we talk about various ways of getting that super critical hands-on practice, including Cisco Modeling Labs. If you want to get that download, just go to kwtrain.com/4ways. Again, that's kwtrain.com/4ways. Now let's jump into this week's video, which is a replay of an IT Insider session we had earlier in the year. Enjoy. We're going to be talking now about MPLS theory, and then we're going to get into the configuration of MPLS, and I think that's going to be a lot of fun for us because we're going to pretend we're service providers and see how that's going to be set up. Now, MPLS, we know that it stands for Multi-Protocol Label Switching. Okay, what does that mean? Well, label switching, it means that we're going to be switching packets like a router. We talk about a router switching packets, not switching in the Ethernet switch context, but making packet forwarding decisions. A router does packet switching using IP addresses, typically, to determine where to send this packet. MPLS, however, is going to use a label. Now, where does that label come from? Well, that label is a 32-bit header, or it's a 32-bit label, I should say. And that little, well, it's in a 32-bit header, but that header gets injected in between a layer 2 and a layer 3 header in a packet. And as a result, sometimes we refer to that as a layer 2.5 technology because the header literally resides between layer 2 and layer 3. Now, what sorts of things do we have in that 32-bit header? Primarily what we're concerned with is label information. I'll show you in fact, I'll show you that topology right now. I think we can make some better sense of this. Before we talk about the labels, one other thing that we might see in some of the output today, you'll see something called EXP, if you want to jot that down. Those are experimental bits. That's quality of service. We've got 3 bits inside of that MPLS label that we can use to mark a priority value. Now, those of you that have taken quality of service training from me, you might remember that we typically mark at layer 2 with a COS value, at layer 3 with an IP precedence, or more likely a DSCP value. And we configure that using MQC, the modular QoS command line interface. Well, if you play around with those commands a little bit inside of MQC, you're actually able to match traffic with a certain set of experimental bits inside of your MPLS 32-bit header, or you can set those bits. using that three-step MQC process. But back to the labels. Let's say that we've got location A and location B, like you see here on screen. And let's just pretend that location A and location B, they're part of the same company. Location C and location D, they're part of a different company. What you can do with MPLS is you can have locations A and B that belong to the same company. You can keep their traffic private just between them, where it's not going to be seen by location C or D. And the same thing, C and D can be isolated from A and B, or we're going to see today that if we want to, maybe they're business partners. We want some of our routes to sort of leak over to that other company. So we can do what's called exporting routes. So again, this is really going to help us out when we have multiple customers. We want to keep their traffic isolated from one another, but we've got the option of sharing some of it if we want to. But to go way back to the origination of MPLS and why it was developed, I remember when I first started working with Cisco routers, it was the original Cisco router, the old AGS Plus router, and some of the subsequent routers after that. Those were, it's cool. They were the first Cisco routers, but they were slow. They did process switching. And that's where the processor gets involved in every single packet forwarding decision. That's not going to scale very well, is it? So what some and it wasn't just Cisco, but the industry realized that when you routed traffic, you made a packet forwarding decision based on IP address information, it slowed things down a little bit. And they discovered that it was going to be quicker to make a packet forwarding decision, not using those long addresses, but by looking at this really short label. So we're going to make packet forwarding decisions using the labels with MPLS. So let's walk through an example here. Notice at location A, we've got a router called the CE router. That's the customer edge router. That's the router that's going to be facing out to the cloud. That's the one connecting into our service provider. And the router at that service provider location, it has a special name. It's called a PE, a provider edge router. So the customer edge is going to communicate directly with the provider edge router. And the language of love spoken between them, it could be OSPF, it could be EIGRP, maybe it's just a series of static routes, who knows? But they have their own little communication path set up. But once we hit that provider edge router, we say, all right, even though we see that this is destined for the IP address that lives over at location B, we're not going to make packet forwarding decisions by examining that IP address every single hop along the way. Instead, that provider edge router, it's going to stamp on inside of that 32-bit header, it's going to stamp on a label. And it's got a table that says, this label is going to get us to this IP network. Now, how did that PE router on the left learn about the IP address of that network going over to location B? It's not attached. Well, here's a term for your notes. It's called LDP, the Label Distribution Protocol. LDP it's a lot like a routing protocol where neighbors exchange routing information. Here, the routers inside of this MPLS cloud, they're going to say, to me, this IP network is going to be is associated with this label, and this other IP address network, this other IP network, it's got this other label. So every router's got this little mapping table. This network equals this MPLS label. This IP network equals this other MPLS label. And here's the key. Let's say that we're going to a network of 10.1.1.0/24. And that PE router on the left says, oh, that's going to be a label of 400. Is it going to be 400 on the next router inside that cloud and the next and the next? No. They have their own unique mapping tables. So the big point here is that label gets rewritten every router hop within that cloud. We're going to rewrite the label. When we're looking at this, we can see this inside of trace route information. We'll take a look at some of this a little bit later today. But we're going to see that it's going to show us two labels. It's going to show us the local label. So if I'm on router B, I'm going to see what router B has labeled this IP network. And then it's going to have a destination label. So I'm going to send it to this other router that's going to have it, that's going to associate with this other label. And again, all these routers, they've learned what labels are associated with networks from their neighbors. Now, the traffic gets labeled, it gets passed through, rewriting the label every single hop until we get to the next to last router, until we get to that router just before the PE router on the right-hand side. Now, it doesn't need a label. It's going to be, if it just sees the IP address, it's talking directly to location B. It doesn't need a label for that. So here's one of the coolest terms in all of networking. Gotta love this term. It's called a penultimate hop pop. Say that 5 times fast. It's called penultimate hop popping. Now, penultimate simply means next to last. So a penultimate hop is the next to last hop inside of this cloud. So the PE router on the right, the router just to the left of that is the penultimate hop. So when it gets to when the packet gets to that router, it's going to pop off that label because that PE router doesn't need it. It's going to make the forwarding decision based on IP address information. Well, technically I should say it's going to remove the outer label. It can still keep the label that says here's how to get to the PE router. It's going to remove the outer label. So that's called a penultimate hop pop. Kind of a fun term. Oh, you also see that the PE router, I've got it labeled as an ELSR, an edge label switch router. That simply means it's sitting at the edge. So we can use those terms interchangeably. Now, I didn't label them, but all those routers inside of the cloud, those are called LSRs, label switch routers. And they're running that protocol that you wrote in your notes, LDP, the Label Distribution Protocol. And one of the great things early on I said is the designer said it's going to be a lot quicker to make forwarding decisions based on labels instead of these big IP addresses. Well, that's not really the case anymore, is it? Now we've got super fast processors inside of our routers. We've got switching technologies like Ceph, Cisco Express Forwarding. So we're practically wire speed. This is giving us negligible, if any, enhancement in performance by doing MPLS. So why do we have it? Why do we keep it around? Well, you can do a lot of cool things with it. You can do, for example, layer 3 VPNs over an MPLS cloud. One of the things I'm going to be showing you today is it's a great way for a service provider to have one protocol, one routing protocol inside of their cloud, regardless of what their customers are running, and send traffic for all the customers using that common, we're going to use BGP to do that, but by using that common protocol within the cloud, they can send traffic for all these different customers, and they can keep it separate. Think about this for a second. Within a corporate network, would you agree with me on this? Would you agree that a lot of networks have decided that, well, there's certainly not enough IP addresses to go around, so we're going to use one of those RFC 1918 addresses. We're going to use some private address space, like I'll use the 10. Network, and I'm going to use the 172.16.0.0/16 network. Can you imagine that multiple companies would make that same decision? They're going to use that private address space within their company. Well, location A talking to location B, that's within the company. We might have a destination IP address of 10.1.1.100 going across this cloud. What if the customer on the bottom, customer that has location C and D, what if they also have a 10.1.1.0/24 network? How do we distinguish between identical networks going across the cloud? we're going to see how that works. It's going to be something called a route designator that's going, or excuse me, a route distinguisher, where we're going to distinguish one route from another. We're going to set up VRF today, virtual routing and forwarding. So I think it's going to be fun. Now, that's an overview of the theory. The rest of today, I'm going to be showing you how to set it up. Before I jump into that, I've thrown out a lot of terms. I know most people have a passing familiarity with MPLS, but any questions? I want to make sure we all feel good about the theory before we jump into the config. So any questions, now would be a great time to ask, and I'll give you a few moments to do that. Any questions? And we've got Ellie joining us as well. That's awesome. Welcome. Steve says, okay so far. Any questions from anyone? Well, let me show you the topology we're going to be working with. Here, and those are the labels. I didn't show you the animation earlier when I was talking. I should have let you watch the packets flow back and forth. But let me show you the actual topology we're going to be working with today. Ali says, I'm good. Excellent. Great to hear. Here's the topology for today. I've got this built inside of CML, Cisco Modeling Labs. And I've got 3 routers that make up the MPLS cloud. So I'm trying to simplify this as much as we can while still showing you how it works. I've got 3 routers inside the service provider's cloud that's going to be running MPLS. And I've got one customer, customer A, and they've got 2 sites. Site 1, that's in the upper left. Site 2, that's in the upper right-hand side of the screen. And what we want to do is to configure, well, first of all, I'm going to show you how to enable MPLS within the MPLS cloud. And we're going to configure multi-protocol BGP within that cloud. And we're going to then peer with the customers. They're running OSPF. I'm already running OSPF within the cloud. And we're going to then redistribute those OSPF networks coming in from a customer. They come into the PE router, the provider edge router. We're going to then label those routes, send them across the cloud, and then pop off those labels and send them to their destination. Now, I considered doing this. I considered adding 2 more customer sites. I thought I could have customer B site 1 and customer B site 2, but I thought about it and I realized that I'm basically going to be spending 10 to 15 minutes entering exactly the same commands that I just entered. So I'll show you how to do it for one customer, and you'll be able to see how you could easily do it for a second, a third, a 10th customer. So let's go out to the live interface right now, and I'll take my face off the screen so we can see everything just a bit better, and I'll show you that topology at the same time. And let's see, Steven says, okay here. Looks like everybody is good. Please stop me. I don't want, we're in no rush today. We're not committed to a timeline here. We're committed to getting results and making sure you understand this. So let's get started, shall we? First, I want you to focus in on that cloud in the middle. It's got those 3 routers, R1, R2, R3. That's our service provider cloud. And before class, I've already set up OSPF within that cloud. In fact, I'm on R1 right now. I'll say show IP route. And just using OSPF, notice that I can see the loopback interface for, well, here's my loopback interface on R1. Here's the loopback interface on R2. Here's the loopback interface on R3. I can see all 3 routers. So OSPF, it is up and running. The next thing we need to do is we need to enable MPLS within this cloud. A couple of options. One option is I could go under each interface that I wanted to participate in MPLS. For example, I'm not going to do it this way, but I want to at least show you how you could do it so you can get it for your notes. If I went into interface, let's see, what is looks like gig 0/0, that's going to be participating. If I went into interface gigabit 0/0, I could say I could say MPLS IP, and I could press enter. That would enable MPLS on that interface. I'm going to do something that I think is a little bit more efficient. I'm going to, just from global configuration mode, I'm going to say MPLS LDP, again, that's the label distribution protocol, MPLS LDP auto config, and press enter. Whoop, that didn't seem to work. Let's see. Oh, I should be in, my bad, I should be in router configuration mode. So I'm going to say router OSPF, my process ID is 1, and I'm going to say MPLS LDP auto config, and I'm going to press enter. Now, what does that do? That is going to enable MPLS on every interface that's participating in OSPF, which is exactly what I want to do. So that's kind of a time saver. So I went in, again, I went into router configuration mode, not global, and I said MPLS, label distribution protocol, LDP, auto config. Now I just need to do that on my other two core routers in the service provider cloud. So I'll say router, OSPF process ID 1, MPLS, LDP, auto config. Awesome. Let's give it a second. We should see, oh, there it is. I wanted to give it a second to see this. It says LDP neighbor is up. 1.1.1.1, yeah, that's R1. So I now have an MPLS, or a label, specifically a label distribution protocol neighbor of R1. Let's go to R3 and finish that up. Again, I'll go into router configuration mode for OSPF process ID 1. And once again, we'll say MPLS, label distribution protocol, auto config. And we'll give it a second. And it should form a neighborship as well. And it does. And in fact, let me bounce back over to R2 really quick, because it has neighbors on both sides. For your notes, here's a command we can give to see what MPLS interfaces are what interfaces are participating in MPLS and what neighbors we have, or if we do have neighbors. I could say show MPLS interfaces. So this is going to show us what interfaces are enabled for MPLS. It's gig 0/0 and gig 0/1. And I said that we should have a couple of neighbors. To see those neighbors specifically, I could say show MPLS LDP neighbor. And here is R1 as a neighbor. Here is R3 as a neighbor. So what have we done? We've done step 1 of all this. Let's see. Somebody's asking, would that work with EIGRP in the core? Yeah, I think so. Let me make sure. Let's do that. I'll say router EIGRP 100. Can I say? What was it? MPLS IP. I'm not saying that I can do it with EIGRP unless there's another command to do it. Honestly, I've never set it up with EIGRP. So I wanted to see. Let's see. I don't see an MPLS command there. Interesting. So yeah, that doesn't appear to be an option. Interesting. I had not looked into that. All right. We do have MPLS with OSPF now set up within our cloud. And the next step, well, before we even do a next step, let's take a look at those labels we talked about. I'm going to go over to R1, and I'm going to do a trace route to the loopback interface on R3. Let's do a trace route to 3.3.3.3. And notice it says for the first hop, when we get to R2, it says label 17 EXP0. Now what that's saying is that we're going to be, that R2 is associating the network that we're headed to with a label of 17. Why is there not a label on the R3 hop? Well, that's our last hop. and the outer label has already been popped off. You see, this is a small network. If I had had one other hop, we would have seen a couple of labels here. But we've already done the penultimate hop pop right here, and we only see the inner label as showing up. But I did want to show you that the label is indeed how we're making those forwarding decisions. And the next thing we want to do is to set up BGP between R1 and R3. To do that, we're going to configure something we talked about that we talk about in the NRC course, and that's multi-protocol BGP or MPBGP. And we're going to do that on R1 and R3. They're going to point to one another's loopback interface. And when we set up multi-protocol BGP, typically if we're using the address families approach, we'll have an address family of maybe IP version 4 to route IP version 4 networks, or IP version 6 to route IP version 6 networks. We're going to see a different type of address family here. Let me show you. Let's go into global configuration mode, and I'm going to say router BGP. You can see in the topology that cloud has an autonomous system of 65. I'm just making sure I'm typing it correctly. Oh, somebody said currently the only IGP that supports this feature is OSPF from the Cisco site. Oh, thanks for sharing that. Yeah, I love it when I learn things too. Like I said, I've never tried it with the IGRP, so yeah, we all learned something today. All right, so router BGP 65,400. I'm just trying to double check to make sure that is correct according to our topology. It seems to be. So let's go into router configuration mode. And I'm going to point to my neighbors. That's what we do when we're setting up BGP. I'll point to now my neighbor here is not going to be just R2. I'm going to point all the way over to the other side of the cloud. I'm going to say my neighbor is 3.3.3.3, and I know how to get there because I'm running OSPF. And I'm going to say its remote autonomous system is also 65,400. Remember, in fact, a little pop quiz for you. When I point to a neighbor and I say its autonomous system is the same as my autonomous system, what kind of BGP, I should say, am I running? There's a couple of flavors of BGP. There's iBGP and eBGP. Which one of those am I running if I say my neighbor's autonomous system is the same as my autonomous system? Yeah, Steven's got it. It's iBGP. So I've got an iBGP neighbor, or I'm setting up an iBGP neighbor anyway. And I'm going to say that that's its quote-unquote remote autonomous system. It's not really remote. It's the same autonomous system I'm using. Next up, I'm going to say for that neighbor, I'm going to be sending updates from my loopback interface. Not a required command. I think it's just a good practice. I'll say my update source is loopback 0. And I'm going to turn off auto summarization. And check this out. For the address family, normally in the NRC course, we would do IP version 4 or IP version 6. I'm going to choose VPN v4. I'm going to say VPN v4. Now, what that is going to do, that's going to configure a routing protocol like BGP to use a standard VPN version 4 address prefix. So we're actually setting up a VPN between routers R1 and R3. We'll say address family VPN 4 and enter that. And now I just need to activate that neighbor. I'll say neighbor 3.3.3.3 activate. Now I need to give a mirror configuration on R3 to point back to R1, so I won't talk as much this time. We'll just get into the configuration. I'll say router BGP 65,400. Whoop, mistype BGP. BGP. There we go. And my neighbor is going to be 1.1.1.1. The remote autonomous system. Let's see, remote autonomous system is not so remote. It's actually mine at 65,400. And I'm going to say that, oh, and I should have an adjacency come up. I'm surprised we don't have an, oh, there it is. Just took a few seconds. You see that I now have an adjacency with R1. Excellent. Now I'm going to say, again, not required. I think it's just a good practice. For my neighbor at 1.1.1.1, my update source is going to be loopback 0. Again, I'll turn off auto summary. I'll set up an address family for VPN version 4. And I'll activate that neighbor, 1.1.1.1. Activate. And we should see a neighbor come up there. There we go. Unicast topology base removed. Adjacency change. All that's looking great. Now, we can confirm that we've got a BGP session set up between these two routers with this command. I can say show BGP VPN version 4 unicast all summary. And it shows, yep, I've got a BGP neighbor. There it is. But right now, you'll notice we haven't exchanged any information. We've got 0 prefixes exchanged. Now, Ali is saying, sorry, but I didn't understand. Why do we need to set up VPN 4? Because we're doing because we're going across MPLS and we're making those forwarding decisions based on labels. We're going to be using a layer 3 VPN, and this is the way I've seen that set up with BGP. We have to use that address family. Notice we were not adjacent routers that were neighbors, and I did not have to set up BGP multi-hop, which is what you would, actually you wouldn't have to do that, would you, within an autonomous system. That's external BGP multi-hop. But it's because we're actually doing a VPN between R1 and R3. And that's the address family type that lets us do that. So let's sum up really quick. Number one, we enabled MPLS in the routers or on the routers in that cloud. We set up BGP between R1 and R3. We've got this virtual VPN set up for it right now that can handle IP version 4 addressing. And what we want to do now is set up VRFs, virtual routing and forwarding instances that can keep one customer separate from another customer. And I talked about the route distinguishers earlier, and I talked about how we could leak one route from one customer over to another customer's routing table. We're going to see how to do that now. Now, I'll go back to R1 to do that. We'll start there. So on R1, I'm going to say IP VRF for virtual routing and forwarding, and I just give it a name. I could say customer, I'll say cust-A. And if I had 10 customers, I could have customer 1, customer 2, all the way through customer 10. These are just logical names for my customers. Now, I'm going to say RD 4:4, and I'm going to explain this command in a moment. Let me enter two commands, and I'll explain what they're doing. I want you to see them first, though. Then I'm going to say route target both 4:4. Now, let's pause for a moment and see what that's about, because if you've not worked with MPLS before, you probably haven't come across those particular commands. The RD, first of all, let me highlight it. RD, that stands for a route distinguisher. And then we also have a route target. Now, we know that an MPLS service provider, they're probably going to be interconnecting sites for multiple customers. And many of those customers, I mentioned this earlier, they might be using the same private IP address space in their company. We might have 4 or 5 customers all using 172.16.0.0/16 address space. How do we keep one 172.16 network separate from another one? Well, that's what the route distinguisher does. This route distinguisher, as the name suggests, is literally distinguishing one route from another. In other words, it can distinguish a route from customer A as being different from a route from customer B, even though they're the same IP address space. Then, when multi-protocol BGP is carrying that route information across this MPLS cloud, it's going to include that route distinguisher information. That's one of the cool things about BGP. We can add on all these extra attributes. We can say, yeah, in addition to carrying network information and next hop information, I want you to carry all this other stuff. And some of that extra stuff that multi-protocol BGP can carry when we set it up for that VPN address family that we talked about, it can carry route distinguisher information. Now, by the way, I said one of our goals is to keep customer A's traffic separate from customer B's traffic, but we might want to leak, or we might want some of customer A's traffic to go to customer B and vice versa. Maybe I want to export from one route distinguisher to another route distinguisher. Maybe I want to import information from one route distinguisher into myself. So that's what this route target says. The both means I'm going to do both importing and exporting between my route distinguisher of 4:4 to myself. Nobody else, just myself. So I'm not going to be talking to any other customers here because those are the same. Now, there's a lot of debate, a lot of confusion about the formatting of that route distinguisher where it says 4:4. There's actually different sort of, I don't want to say industry standard, but there's some accepted formats for how that RD should look. I've seen it where people use autonomous system numbers in that route distinguisher. I've seen where they use IP addressing. You can really make it whatever you want, though. It's not going to break it if you just make up a number, which is kind of what I've done here. The route distinguisher is basically just a number that's going to distinguish one customer from another. So to keep it simple, in our example, I just said 4:4 for customer A. That's it. All right, that's an overview of what the route distinguisher and the route target is all about. Now, so far all of our work has been focused inside of our cloud. Again, number one, we enabled MPLS. Number two, we set up multi-protocol BGP for the VPN version 4 address family. Now, I've created a VRF, which says the customer A traffic is going to reside inside of this VRF. It's going to have its own routing table that would be separate from a customer B routing table, as an example. Now, I'm going to get ready to connect out to an actual customer at this point. Oh, we got a question I saw coming in from Steven. My understanding is that when BGP is carrying the routes from R1 to R3, the routes have to have an extra tag so it knows the customer routes are for BGP IP version 4. It can't carry tags, but the VPN version 4 can carry those. Yeah, that address family, yeah, that's my understanding as well, Stephen. Yeah, that particular address family can carry the route distinguisher information that would not be carried by something like OSPF, as an example. Yeah, that was that's one of the cool things about BGP. Now let's get ready to connect out to a customer. Now, if you look at that topology really closely, and I'm doing the same thing here, it looks like we're leaving on gigabit 0/1 going up to customer A site 1. So what I want to, and it's currently shut down. So let's go into that interface. I'm going to go into interface gigabit 0/1, and I'm going to say, hey, well, let's no shut it first. Let's bring it up. No shutdown. And I'm going to say, I want you to belong to the VRF instance that we've called customer A. All right. I'll say IP VRF forwarding customer -A. And I want to give it an IP address. If you look at the topology, it looks like we've got an IP address for that interface of 192.168.1.1. 192. I'm so used to typing 172.16, 192.168.1.1, 24-bit subnet mask. Let me just do a real quick sanity check. Can I ping customer A? Can I ping 192.168.1.4, it looks like? No, that's a concern. I was expecting that one to work. Oh, I'm 1.1, not 1.4. My bad. I looked at I was trying to look at the topology so hard, and I looked at the wrong number. Let me go in and fix that really quick. What did I say? It's gigabit 0/1. Yeah, that IP address. Oh no, I did do it right, didn't I? It is 1.1. You might see a typo that I made. Do I need a VRF in the ping? Yes, you're absolutely right. I forgot. Yeah, we're talking about the VRFs. You're absolutely right. We do need that. In fact, at this point, router R1, it should have a couple of routing tables, just to make your point. It should have a routing table that's the global routing table, and it should have a routing table specific to customer A. So yeah, that was a great catch. I'm going to say show IP route. That's going to be the global routing table, but not the one specific for customer A. If I want to see the one specific for customer A, it's show IP route VRF customer A. And yeah, that you're absolutely right. That proves it. That's how I can get to that network. That's how I can get to that network, because it's in that routing table. Now, we see we do have a couple of different routing tables. Now, let's configure OSPF on R1 so it can peer, it can form a neighbor relationship over with the customer A site 1. And once I get those routes coming in from customer A, site 1, I'll be able to redistribute those into BGP. So let's do that. I'll say, oh, yeah, I never did go back and do the ping. I proved that we could, but I didn't do it yet. Yeah, we want to do a ping. And notice we can specify a VRF. Ping VRF. And the VRF name is customer, or the instance is customer A. And then I'll try to do a 192.168.1.4. Oh, I misspelled VRF. Boom. I love it when a plan comes together. All right. Now let's set up OSPF so that we can peer over to customer A. Let's go into global configuration mode. And I'm going to say interface gigabit 0/1. That's the one that connects up to customer A. And I'll say IP OSPF. And I'll just say process ID 2. That's what I'm running on this router. And notice that customer A, it says, if you look at the topology, it says it's an OSPF area 2. So I'll specify that area. We should get an adjacency. Yep. Notice we went to a full adjacency right then. Perfect, perfect. Now, if I say show IP route VRF customer A, I should be able to see, yeah, you see this 4.4.4.4 that I'll learn to be OSPF. Yeah, that's the loopback interface on that customer A site 1 router. So I'm talking to that customer via OSPF. Great. Now I want to go do the same thing on R3. I want to set up an OSPF neighborship between R3 and customer A site 2. So let's go into global configuration mode again. I'll say, oh, actually we haven't even set up VRF yet. We'll do the whole thing here. I'll say IP VRF customer A is the name of our VRF instance. The route distinguisher is 4.4. The route target in both directions is just going to be with 4.4. It's just going to be with ourselves. Let's go into interface, double checking the topology, interface gigabit 0/1. We'll do a note shutdown. IP VRF forwarding. For customer A on that interface. Let's give it an IP address 192.168.2.1, 24-bit subnet mask. IP OSPF process ID 2. And I'm going to be in, that interface is going to be in area 2. And we just had a neighborship come up. Excellent. Show IP route. For our VRF instance of customer A. Have I learned anything from customer A site 2? I sure have. 6.6.6.6. Yeah, I learned that via OSPF. So now the cloud is talking to the customers are talking to the cloud, but we still have to add some connective tissue right now. Oh, did somebody say I typed in the wrong IP address? 196. I'm sorry, Steve. What was the wrong IP address I typed in? Let's see, 192.168. I'm just double checking my topology. I don't want to. Yeah, the challenge with doing a demo that's this long, if you type in one thing incorrectly on along the way, it messes everything up. Somebody said 172.16.2.3. Ah, you're so right. It was the wrong IP address. Thank you for that. I did indeed type in the wrong IP address. So let's go back and fix that. Interface gigabit 0/1. IP address is 192.168.2.3. And again, that's with a 24-bit subnet mask. Neighbors down is going to come back up. It did not come back up. Huh. Thinking about why that might have happened. Let me bounce the interface. Okay, now we're back up. Just didn't give it enough time. Okay, thanks for that. Yeah, I did type. You know, it actually probably would have worked, but yeah, I want to stay consistent with the topology. So thanks a ton for everybody that pointed that one out. All right, now where were we? We said that at this point, R1 and R3, they're acting as our MPLS PE. They're the provider edge routers, the edge LSRs. And they also have an OSPF neighborship with our customer edge routers. However, we want those OSPF learned routes coming in from the customer, we want those to be sent across our MPLS cloud using multi-protocol BGP. So the next thing we want to do is to redistribute on R1 and R3. We want to redistribute, in fact, we'll mutually redistribute OSPF into multi-protocol BGP and vice versa. So actually, do I need to do vice versa? No, I actually don't think I do. I think I just need to redistribute. I need to redistribute OSPF into BGP. So let's do this. Let's go back to R1. Router BGP 65,400. And I'll say for the address family to get into the right configuration mode for here, I'm going to say the address family is going to be IP version 4. for VRF customer A. I'm going to redistribute OSPF process ID 2. Let's do the same thing on R3. Router BGP 65,400. Redistribute OSPF 2. Now, let's see if BGP on our provider edge routers, let's see if they know about the loopback addresses of our CE routers. So let me go back to R1 really quick. Let's do a show IP BGP VPN version 4 VRF customer A. Beautiful. 4.4.4.4, that's customer A site 1. 6.6.6.6, that's customer A site 2. So we know about those routers. Awesome. The redistribution worked from OSPF into BGP. That's carrying the route information across the cloud. But like I was saying earlier, we probably do need to go in the other direction. We need to take those BGP routes that we clearly now know. Let's redistribute those back into OSPF so that the customers, they can see each other. So on R1, I'll go into router configuration mode for OSPF process ID 2, and I'll say redistribute BGP 65,400. Now, before I give the next, let's see, comment from Steven. I would have thought that both ways, yeah, you're right. Yeah, it is both ways. Yeah, I think earlier I wasn't thinking far enough ahead earlier. I said, yeah, we can go in just one direction. Well, yeah, I was thinking that'll let all the routers in the cloud know about these networks. But yeah, you're totally right. We need to let the customers get to each other, obviously. So yeah, you're right. And that's what we're doing now. We're gonna make sure and do mutual redistribution. Now I'm saying redistribute BGP 65,400. Now the next command or the next parameter I'll say I probably don't need. It's an old habit that I've used literally for decades. Some new versions of iOS don't require this, but I just always do, just to be safe, I guess. I always give the subnets command. Can anybody tell me in the chat what's the purpose of this subnets keyword? Why did I say redistribute BGP 65,400 subnets? What would have happened if I did not use the keyword of subnets? Yeah, Steve says all the subnets are going to be included. Yeah, if I don't give that on some earlier versions of Cisco iOS, you know what's going to happen? It's only going to advertise a classful network, not the subnets. Now, I've noticed in more recent versions of Cisco iOS, it just kind of does it automatically. It knows that, oh yeah, they probably want the subnets also, and that's included. But just to be safe, just old habits die hard, I still always give that. Let's go to R3 and do the same thing. We're getting close to the end, folks. On R3, I'll say for router OSPF process ID 2, I'll redistribute BGP autonomous system 65,400 subnets. And drum roll, please. Let's go to one of our customer sites. Let's go to customer A site 1, and let's check the routing table to see, do I know how to get to customer A site 2? In other words, do I know how to get to 6.6.6.6? Let's try. Let's do a show IP route. Can I get to 6.6.6.6? I can. Look at that. It says I learned it via OSPF. I learned it via another area, because the area of the MPLS backbone, that was a different area. But yep, I have learned it. So can I ping? Here's the final test. Can I ping over to 6.6.6.6? And I can. I can go across that service provider's cloud. And the cool thing is, we could have had two other sites here, and they could have had identical, this is the thing that's so cool about this, they could have had identical IP addressing. And even if they did, their routing tables would have been kept. Separate. So that's one of the benefits of using MPLS. Even though performance isn't that big of a deal anymore, it's still great that we can have all these different customers isolated. Now, we didn't play with route targets. I wanted to keep it simple, but with the route targets, I could have let some customer networks go into other customer networks. So you're not limited to keeping everybody isolated if you don't want to, but you certainly can. So I thought that might be a fun look at how, in a service provider's mindset, we might see how we could peer with different customers using MPLS and multi-protocol BGP.